Okay, everybody look at this. The sinusoidal function, suppose you call the signal as x of t, okay? The sinusoidal function is represented as sine omega t, okay? Since we already have dealt with the exponentials in the previous session, okay, it would be easier for us to find out the Laplace transform of sine omega t if we express sine omega t in terms of the exponential. It's not only any, it's not only the sine omega t, any sinusoidal for that matter. It could be sine omega t or it could even be cos omega t. So how to express sine omega t in terms of the exponential? It is given as e power j omega t minus e power minus j omega t divided by 2j. Okay. Similarly, if you are given cos omega t can be expressed in exponentials in the form of e power j omega t plus e power minus j omega t by 2. See the difference here. Okay. So important is you're not supposed to miss this j in the denominator along with 2. Fine. Now we shall apply the what? Laplace transform on this because we have been obtaining the Laplace transform of the sinusoidals. Okay, so what is Laplace transform of x of t? Okay, so what is Laplace transform of x of t? It is integration 0 to infinity x of t e power minus st, okay, with respect to t. Fine. Now, what is x of t? X of t is sine omega t, okay, e power minus st dt. But to make the thing simple, what we're doing, we are expressing this sinusoidal in terms of the complex exponentials. Okay, how can we do that? E power j omega t minus e power minus j omega t divided by 2j. Okay, this is what it is along with the exponential in the equation. This is how the things look like. Now, how can we rearrange this further? So therefore, what is this? Laplace transform of x of t can be written as x of s, okay, is equal to 1 by 2j can be kept outside, okay, and we can have two integrals e power j omega t e power minus st dt minus 0 to infinity e power minus j omega t e power minus st dt. This is how we can rearrange the terms. Okay. Now you have two exponentials as we have done in the previous uh, derivation. What is that? If you have exponentials, okay, combine those exponentials. Fine. To have one exponential. So in both the terms we have two exponentials. So combine them into one exponential. So how to do that is this 1 by 2j, okay, 0 to infinity e power. How we can write this? I need omega plus, yeah, s plus omega stuff. Okay, so I'll write this as minus of s minus j omega t. Is this okay with you? Because I wanted s minus j omega term there. Okay. So how would I write this? This minus would be taken common. So it would be written as s minus j omega into t dt. So this is how we have arranged it. Okay. Then this can be taken as e power minus s plus j omega. t dt. So this is how the things look like. Okay, in the previous class we have seen what is going to be the integral of e power minus at. So what is a here? S minus j omega is a. What is a here? It is s plus j omega. So this is in the form of decaying exponential now. Everybody understand that? So this is in the form of decaying exponential. So what is that we know about decaying exponential? So in the previous class itself we have seen, okay, so that is if you have a decaying exponential. See, this is uh, growing exponential. This is decaying exponential. So we have seen in the last class what is that if you have e power minus at, okay, what is the Laplace transform of that given as? It is given as what? 1 by s plus a. Okay, so straight away we can do that here. Fine, so it's s minus j omega. Let's see it. It's not a is not s minus j omega. A is j omega here. A is minus j omega here, because you have to see this x of t when there is an exponential here, everybody. So this is not a, mind you, this is not a. Well, this could have been a if there is if there is an exponential e power minus st, but that e power minus st is combined within it. Everybody understand that? Okay, so what we can do, you can further go and integrate this, that is e power minus s minus j omega t divided by minus s minus of s minus j omega. Okay, apply the limit 0 to infinity. Minus, what would this be? This would be e power minus s plus j omega t, okay, divided by minus s plus j omega. Okay, the limits applied is 0 to infinity again. Fine, so if you see this after the limits applied, okay, so this should look like 1 by s minus j omega minus 1 by s plus j omega. Okay with that? Now we take the LCM. What is the LCM? We can take that as s minus j omega s plus j omega. Don't forget to have this 1 by 2j outside. Okay, so it would be s plus j omega minus s minus of minus j omega. So this is how things are going to look like. Okay, what the denominator, what is this in the form? S minus j omega and s plus j omega. A minus jb into a plus jb. What is it going to be? What is it going to be? It is going to be equal to s square plus omega square. Okay, a minus b into a plus b. You can see it that way. Okay, so this can be written as 1 by 2j times, okay, so this and this s gets cancelled, so you'll have 2j omega in the numerator. Okay, in the denominator you'll have s square plus omega square. Why is that? Since uh, a minus b into a plus b is a square plus b square. Okay, so what happens? This 2j and 2j get cancelled. So what you'll be left with? So you'll be left with uh, what? Omega by s square plus omega. So what is this? This is Laplace transform of sine omega t. Everybody understand this? So this is how we can find the Laplace transforms of the basic signals. Now, I'll give you a list of such basic signals. Suppose we have cos omega t. Okay, what we have to do? You have to do in this form only. Okay, so likewise, we can have the Laplace transform of many basic signals or combination of basic signals. So we shall see such a standard list of Laplace transform. Okay, so you can always have this as a reference when you're asked to solve the problems. Okay, so take the heading as, again I'm not going to solve it for cos omega t and the combination of these basic signals. What we'll be doing is we shall list them. Okay, so how to do that? Okay, so just copy this. Important transform pairs. Transform pairs means what? I'll just be giving you. Transform pair is this. If you have x of t, suppose. If you have x of t, the Laplace transform of this is going to be x of yes. So x of t and x of s are called as transform pairs. Why are they called as transform pairs? Because if you have x of t, apply Laplace transform on this, you will get x of s. And if you are in Laplace domain, apply Laplace transform on inverse Laplace transform on x of s, you'll get x of t. So if you are given x of s, we can obtain x of t by applying the inverse transform. If you are given x of t, you can obtain x of s by using the Laplace transform. Okay, inverse Laplace transform and Laplace. That's why with one given, the other can be obtained. That's why these two are called as the transform pairs. Understand that? So we shall just see what is that we have seen so far. Everybody, okay, just copy this list. Everybody just copy this list. Okay. Now, what is the first? Okay, let's just go on. Suppose in this list I take okay. Suppose the first signal is delta of t. What is the Laplace transform of delta of t that we have seen? That is 1. Second one. What is Laplace transform of u of t? U of t Laplace transform is 1 by s. Similarly, we have seen the Laplace transform of a ramp signal which is given by t. What is Laplace transform of this? Laplace transform of this is 1 by s square. Fourth one. Which one did we see after this? We saw e power minus at. What is e power minus at? It is decaying exponential. So what is the Laplace transform of this? It is 1 by s plus a. Is the Laplace transform of decaying exponential. Fine. Then the fifth one. What is that? It is the sinusoidal. Sine omega t, something that we have seen just now. So what is the Laplace transform of this? It is omega by s square plus omega square. Understand? So this much we derived. Next we have not derived after this, but if it is asked, you have to be deriving it. But I'll give you the list. You can derive and see that. Okay. So if instead of sine omega t, what if you are given cos omega t and asked to find out the Laplace transform of this. Okay, so what you would do is in place of omega you will have yes in the numerator and the denominator would be same. So this is something that you can derive and see. Okay, so sin omega t is omega by s square plus omega square, but cos omega t is s by s square plus omega square. See the difference. Okay, now we shall see the combinations of these basic signals. What does that mean? Suppose, see here, now instead of t, what if we have powers of t is the question. See here, we have t, it is 1 by s. If we have t, the Laplace transform of t is 1 by s square. What if we have powers of t is the question. If we have powers of t, the Laplace transform of that is given by the power factorial. The power is n, right? So factorial of the power divided by s to the power plus 1. Okay, so this is what is the Laplace transform of powers of t. Okay, similarly, what if you combine, everybody see here, what if you combine a ramp function with decaying exponential? So see here, what is ramp function? It is 1 by s square. What is decaying exponential? It is 1 by s plus a. So if you have t along with e power minus at, so that combination would give you the Laplace transform. See here, for 1 e power minus at, it is 1 by s plus a. Since t is there along with it, okay, so the denominator needs to have a power of 2. 1 by s plus a square. If you have e power at, it is 1 by s plus a. If you have t into e power minus at, it is 1 by s plus a square. Is that okay with you? Now, similarly, let's just increase this list by having two more transforms. Yeah. What is it? Ninth one. Suppose if we have sine omega t, it is omega by s square plus omega square, right? What if you have e power minus at along with sine omega t? Okay, what you have here, if e power minus at is there, if e power minus at is there, it is s plus a, 1 by s plus a. That means uh, wherever s is there, that needs to be replaced by s plus a. Understand that? So that is the idea. So in the denominator, in the numerator, we have omega. Okay, so in the denominator, wherever s is there, you have s plus a. Okay, so instead of s square, you'll be writing s plus a whole square plus omega square. This is how e power minus at sine omega t looks like. Okay, suppose you have e power minus at with cos omega t. What we can have? Anybody? In place of s, we need to have s plus a. What is cos omega t? Cos omega t is s by s square plus omega square. So wherever s is there, okay, since e power minus at is there along with cos omega t, the s has to be replaced by s plus a. Okay, so in the numerator we have s, that needs to be replaced by s plus a, and in the denominator we have s square, so that needs to be replaced by s plus a square plus this. So these are some standard basic signals and their uh, combinations. Okay, and what are the Laplace transforms of these? Fine. So you need to have this list for as your reference, because it would be helpful if you have this list with you. Okay, not that you'll not be asked to derive this. You may be asked to derive this. Okay, so after derivation, without derivation also you should be able to remember this. Okay, because these are all basic signals. Fine. So now we shall see the properties of Laplace transform. So these are the Laplace transform for basic signals. Okay. So if they ask us to find out some combinations of this, we can make use of these results. Now, there could be problems like this. Just see here. The problems like this. Suppose if they ask, obtain the Laplace transform of some signal, say, um, suppose some signal x of t, okay, using the properties of Laplace transform. So some problems would come like this. So you have to be using the properties of Laplace transform only to obtain the Laplace transform. Understand? So in such circumstances, we need to be knowing the properties of Laplace transform. Everybody understand that? So in some cases, they'll ask us to obtain the Laplace transform by using the properties. So for this, what we need to know? So for this to be done, we should know the properties of Laplace transform. Okay, so that's why we are taking the properties of Laplace transform now. Okay, so this, take down the heading as what? Properties of everybody Laplace transform. We are not deriving it, mind you. Okay, due to time constraints, we're not deriving the properties. I'll be giving the list of properties. Okay, but you have to learn deriving it yourself. Okay, so the derivation you'll find in any textbook, any standard textbooks for network theory or network analysis. Okay, so that you using that, you need to be seeing the derivations of Laplace transform. So the assignment is you take down this as assignment. Okay, what is the assignment? uh, Derive all the properties, derive all the properties of Laplace transform. Okay, so this is the assignment for you. I'm not doing this here in the class. Okay, but this is expected. They may ask in the exam. Okay, that's why I'm particular. Uh, okay, for this assignment to be done. Fine. So this derivation can be asked in the exam, but I'm just giving you the list of these properties. Okay. So what is the first property? So the properties that I'm listing, more or less all the transforms would have these properties. Okay. The first property that we are seeing is linearity. Linearity property. What is linearity property telling you? Suppose instead of having two signals, instead of having one signal, what is that? Okay, see here, if you have x of t, okay, if you have x of t, the Laplace transform of x of t is what? X of s. Okay, then Laplace transform of what? A x1 of t plus b x2 of t is given by what? Is given by here. A and B are scalars here. The A and B that I am writing, everybody just understand this. If you have x of t, it is x of s. So instead of x of t, if we give you two signals which are scaled, if we give you the sum of two signals which are scaled, understand that? So this is a signal x1 of t, but it is scaled by a constant a, scalar a. What happens to x1 of t? If you have a as a number greater than 1, then x of t would get amplified. If a is less than 1, then x1 of t is what? What happens? What is the opposite of amplification? It is attenuation. Understand that? Okay, so this is some scaling factor, so depending on that, the amplitude of x1 of t would be decided. Understand that? Now similarly, we have another signal x2 of t. So that x2 of t is also a scaled signal. Okay, so those two scale signals are sum. So what is this? Instead of giving you x of t, what if you are given the sum of two scale signals? What should be the Laplace transform of that? So the Laplace transform of that look like here. If there is a scalar, so these two are scalars. Okay. They are scalar, some numbers. Okay, so these scalars need to be kept out, and you have to be applying Laplace transform only on what? X1 of t. Get this point? You have to be applying Laplace transform only on x1 of t. Keep again the scalar b out. Apply Laplace transform only on x2 of t. So what does it look like? It looks like a x1 of s plus b x2 of s. So this is what is the linearity property tells us. So that means if you have a signal along with a scalar, separate the scalar and apply Laplace transform only on the signal. Okay, so this is one property of Laplace transform, wherein you can separate the scalar and apply Laplace transform only on the signal. That is what is happening. See here, if you are given this, okay, what they're doing, they keep the scalars out, okay, and apply Laplace transform only on the signal x1 of t. So this is a signal, this is a signal, this is also a signal. Get that point? So this is linearity property. So we shall use this property to solve problems. Fine. Now, second property, everybody take down. Second property is time shift property. Time shift property. So how does it look like? Time shift property. What is time shifting? So if you have x of t, the Laplace transform of this is given by x of s, as we have seen here. So this is one way of representing the application of transform. This is another way of representing the application of transform. You can use any one. I'm using both here. So to just let you know that, so this type of representation can also be used, or this type of representation can also be used. Laplace transform being applied on x of t, okay, would give you x of s. Similarly here, Laplace transform being applied on x of t would give you x of s, and applying inverse Laplace transform on x of s would give you x of t. So these are transform pairs I told you, right? So this is how we write. This also can be one way of representing the application of the transform. So if x of t is, if a Laplace transform of x of t is x of s, then we can say Laplace transform of x of, see here, t minus t naught is what? Is the question. Okay, this is what is time shift, shift in time. So this is, we are shifting. Okay, so this time is being shifted by t naught second to the right. This is right shift of the signal. Okay, so when it would be right shifting, when it would be left shifting, we're not going in the details of all that. So we'll be learning all that in signals and systems, I've been telling you. But understand that this is time, t is time, and this is time shifted signal. That means if x of t starts at 0, means x of t minus t naught would start at t naught. Everybody understand that? T equal to t naught. So if such a time shifted signal is there, then what you can do is this. See, which is the basic signal here? X of t is the basic signal. Okay, so you need to know the Laplace transform of the basic signal. X of s is that. So along with the Laplace transform of the basic signal, this exponential needs to be there. What is that? E power minus t naught. Yes. Everybody understand it? Okay, I'll be writing it clearly. E power minus t naught s into x of s. What is this x of s? X of s is the Laplace transform of x of t. So the signal is x of t, so we need to know the Laplace transform of x of t, that is x of s. Understand that? So what is the Laplace transform of x of t minus t naught? Then Laplace transform of x of t minus t naught is x of s being multiplied by an exponential x of t, x of minus t naught s. For example, I'll just give you some example. You can take this example if you want. See here? You have u of t, you know u of t, right? What is the Laplace transform of u of t? So this is first. Suppose if I ask you the Laplace transform of u of t is a step function, unit step function. So it is 1 by s. Then what is, suppose I'll ask you, what is Laplace transform of u of t minus 2? I'll ask you. So this is shifted unit step function. What is Laplace transform of this? So from the time shift property, what you should understand, what is the Laplace transform of u of t, that needs to be known. Along with that, we need to have an exponential. What is that exponential? E power minus 2s into, what is Laplace, which is the basic signal? Basic signal is u of t. U of t is being shifted, right? So basic signal is u of t. What is the Laplace transform of the basic signal? It is 1 by s. So if you have a signal u of t, then it is 1 by s. If you have a time shifted signal, then it is 1 by s into e power minus 2s. So this is where these standard transforms would be of use. Everybody understand? So if we know u of t is one, Laplace transform of u of t is 1 by s, then only we can go for obtaining this by using the properties of Laplace transform. Otherwise, no, because we need to know the basic signal. Basic signal is u of t. That u of t is being shifted. Okay, so you need to know the Laplace transform of u of t. Since it is shifted, this exponential should accompany there. Is everybody okay with that? Similarly, we have the time shift we saw, right? Similarly, we have another shift here. What is that is called as, see here, everybody just make a note. Third one we are going for. As we did time shifting, there could be shifting in S domain also. Shift in S domain. So that means if Laplace transform of x of t is x of s, then we saw time shift here, right? This is time shift. Now it is talking about shift in S domain. That means this is S domain. What if you have a shift in S domain? Is the question. Understand that? Suppose you have shift in S domain. That is, suppose say you have S minus S naught. Earlier you had X of t minus t naught, right? Because it's time shift. Shift in time domain. This is shift in S domain. Okay, where is the shift? S minus S naught. Minus S naught is the shift. Okay, so if you have a shift like this in S domain, what would be your time domain signal is the question. Okay, so the time domain signal would be x of t along with an exponential e per s naught into t. See, if there is a shift in time domain, then the exponential will have minus power. Okay, so if you have a shift in S domain, then the exponential accompanying the time domain signal would be having a positive power. Is this understood? So it is e power S naught t in time domain. Understand that if you have a minus S naught shift in S domain. Is that okay with you? I've been telling you that we're not deriving all this, but derivations are important from examination point of view. So you'll be deriving it and you'll be presenting it to me as the assignments.